In this lecture, we'll discuss the Rankine cycle. So, now that we have discussed the properties of a pure substance that can be in different phases, such as water, that can be in liquid and vapor phase, we can now see how we can use such pure substances which can be in different phases for engineering applications. And the first application that we are going to look at is a power cycle. In particular, a vapor power cycle, that is to run a heat engine using, let's say, water as the working substance, and water can be in liquid and vapor phases. So earlier we have considered a Carnot heat engine and showed that the efficiency of a Carnot engine is independent of the working substance. So if we have a Carnot engine, that is a heat engine that is operating on a Carnot cycle, then we have shown that the efficiency of a Carnot engine, let's say two such engines E1 and E2 that operate with different working substances, would be the same. So if we have two heat engines E1 and E2 operating on a Carnot cycle, and let's say E1 has a working substance that is an ideal gas and E2 works on water as the working substance, then both engines will have the same thermal efficiency, of course, provided both these engines absorb and reject heat at the same high and low temperatures. Now, irrespective of the choice of the working substance, provided it is a pure substance, the Carnot cycle can be depicted on a TS diagram such as this. So the working substance is initially at state 1, then through a reversible adiabatic process it is compressed to state 2, and because the process is reversible and adiabatic, it is isentropic, and therefore entropy of states 1 and 2 is the same. In the next step, heat is absorbed at constant temperature, let's say TH, and isothermally this heat is absorbed, and let's call that heat QH, from a thermal reservoir at temperature TH, and then from state 3 to state 4, the substance undergoes a reversible adiabatic expansion, and again the entropy does not change during this process, and the substance attains a state 4, equilibrium state 4, and from 4 to 1 heat is rejected, let's say QL, at a low temperature, that is at fixed temperature TL. So a Carnot engine that works on ideal gas or let's say steam, both of these engines can be represented on a TS diagram such as this. So this heat engine, it gains entropy QH over TH from this step, from 2 to 3, that is during heat transfer from high temperature, the entropy gained by the system is QH by TH, but then during this process of heat rejection, it dumps this amount of entropy to a low temperature reservoir, and the net effect is that once the cycle is complete, there is no change in the entropy because entropy change for the cycle is 0. Therefore, QL over QH is equal to TL over TH, and the thermal efficiency, that is also the first law efficiency of this Carnot cycle, is the work output over the heat input, and that is equal to 1 minus QL over QH, and this from this equation is 1 minus TL over TH, where TL and TH denote the absolute thermodynamic temperatures of the reservoirs from which the heat is being reversibly accepted and rejected. We have already seen earlier how to operate a heat engine on a Carnot cycle using a gas such as an ideal gas. Now that we have studied the properties of a pure substance such as water that can be in liquid and vapor phases, we will now consider operating a Carnot cycle using a pure substance such as water, in particular using steam. So the Carnot cycle can be realized in various ways if we want to use water as the working substance. So if we look at the TS diagram for water, this is our saturation dome. So if we want to have a Carnot cycle such as this for water, we can have different ways. One way is this. So if we choose this cycle for operating a Carnot heat engine, then at point 1 we have a liquid vapor mixture, and this liquid vapor mixture is compressed until state 2 is attained. At state 2 we have a saturated liquid. Thereafter heat is absorbed at constant temperature during vaporization from saturated liquid state at 2 to saturated vapor, that is at state 3. Thereafter, the saturated vapor is expanded isentropically, that is through a reversible adiabatic process, to state 4, that is at a lower temperature and lower pressure. Finally, from 4 to 1, we have condensation, and the quality of the mixture decreases and the substance is brought back to state 1. Such a Carnot heat engine can be based on a piston cylinder arrangement or a flow process through various devices, such as a steam power plant, whose basic operation we have introduced during the introductory lectures of this course. However, irrespective of how this Carnot heat engine is realized, in both cases, engineering of equipment required for this process going from 1 to 2 is practically challenging, because the equipment would require to handle a wet mixture throughout, which is practically very difficult due to a large decrease in specific volume as the substance goes from state 1 to state 2. So this is the main practical challenge in approximating the Carnot cycle using steam, because compressing a wet mixture is practically challenging. Note that the benefit of using a liquid vapor mixture to operate a Carnot heat engine is that the heat addition, that is from 2 to 3, and heat rejection from 4 to 1 occur during the vaporization and the condensation processes, which are naturally isothermal. However, this does not exclude the irreversibilities in a practical system due to heat transfer over finite temperature difference. But theoretically, if there's an infinitesimal difference in this vaporization temperature and the temperature of the high temperature thermal reservoir, then one can operate such a cycle or a heat engine reversibly. Similarly, if we have this heat rejection from 4 to 1 occurs over a small or infinitesimally small temperature difference, then the heat engine would operate reversibly. Thus, except the compression process, all other processes are realizable, though in reality they will also be irreversible. There are other choices that one can have for operating a Carnot cycle on this TS diagram. So another way to do it is, let's say, this cycle. So this cycle shown in blue color is another way we can implement the Carnot cycle, but it's even more complex than the previous cycle, and that's because here the heat addition partly takes place from this state to this state at constant temperature and constant pressure. But from here to here, that is, let's say from this point A prime to point 3 prime, the temperature is fixed, but the pressure continuously decreases. Therefore, in practice, this is even more challenging than performing this Carnot cycle. So based on this discussion, we conclude that the Carnot cycle is not possible to realize given the various limitations of engineering. Therefore, we need to consider changes to the Carnot cycle to make it realizable. Of course, with the irreversibilities that are associated with real processes. So we have seen that the main engineering challenge in implementing the Carnot cycle using steam, let's say, is to compress the wet mixture in a Carnot cycle. To overcome this engineering challenge in compressing a wet mixture in a Carnot cycle, a modification is made to the Carnot cycle. And this modification results in the Rankine cycle. So in the Rankine cycle, the modification is that if this is the Carnot cycle that we considered earlier, now the heat rejection step, that is from this state to this state, is continued until this saturated liquid state is attained. So now we'll call this state as state 1. This is the state 4. So now we have a liquid, in particular a saturated liquid, that we need to pump to a higher pressure. So this liquid is pumped to state 2 at higher pressure, and in the ideal cycle that is done through a reversible adiabatic compression. Therefore the entropy remains the same at states 1 and 2. Thereafter, we have a subcooled liquid or a compressed liquid at state 2, and this liquid is fed to the boiler and it is heated, and first upon heating at a higher pressure, so this is an isobar at higher pressure, so it attains the saturated liquid state at higher temperature and higher pressure, and thereafter heating is continued until we have state 3, which is saturated vapor. And thereafter the same process of reversible adiabatic expansion of the substance takes place, and from 3 to 4 we go isentropically. So the only modification to the Carnot cycle we see is for this process that we continue our condensation until we have a saturated liquid, and this part is different from 1 to 2 prime because now instead of heating only the liquid vapor mixture, we also have to heat this subcooled liquid or the compressed liquid. Note that the Rankine cycle is also an ideal cycle, but it can be closely approximated in a practical system, and the Rankine cycle is a model for the simple steam power plant. For a simple steam power plant, the 4 processes of the Rankine cycle can be shown on this diagram, where initially the working substance, that is water, for a steam power plant is at the saturated liquid state at low pressure and correspondingly low temperature. Then a pump is used to increase the pressure of this substance, and this is our state 2, that is over here. Then the liquid at high pressure is fed into a boiler where it is heated, and the liquid vaporizes and exits the boiler as a saturated vapor, and this is our state 3. This saturated vapor is fed into an adiabatic reversible turbine in the ideal cycle, and it gets expanded lower pressure at state 4 through an isentropic expansion process. And thereafter, in the condenser section, heat transfer takes place at a constant pressure during condensation, and heat is rejected, whereas heat is absorbed in the boiler at constant pressure from states 2 to state 3. So here we have shown a flow system to execute this Rankine cycle, but the Rankine cycle can also be executed in a cylinder piston arrangement, just as we have looked at a cylinder piston arrangement for operating a heat engine, but this time the substance is the vapor or the liquid vapor mixture. So in either case, if we have a cylinder piston arrangement where the Rankine cycle is executed, or we have a flow system such as the steam power plant which executes the Rankine cycle, the area that is enclosed by this cycle on the TS diagram, that is this, corresponds to the work done by the heat engine that is executing the Rankine cycle. This is because, as we have seen earlier on a TS diagram, if we have any path, then the area under that path corresponding to a reversible process denotes the heat that is transferred to the system, that is integral T ds. And in this particular case, if we look at the area under this path, that is going from 1 to 3, then that area is the heat that is transferred to the system, that is QH, whereas this particular area that is under this curve 4 to 1, this is the heat that is rejected to the low temperature reservoir. So the difference of these two areas is the area enclosed within the cycle, and that is the work output of the heat engine. So the area shown in the green color is the work that is done by the heat engine, and this is irrespective of how this Carnot cycle is executed, either in a piston cylinder arrangement or in a flow system. Another way to see this is that if we consider a piston cylinder arrangement, then the work done by the system is PdV. Therefore, if we combine the first and the second laws, we have du is TdS minus PdV. And for a cycle, if we integrate, we have integral of an exact differential over the cycle is 0. Therefore, PdV integral, which is the work, is equal to TdS. That is essentially the heat that has been added to the system reversibly. Therefore, the area enclosed by a cycle on a PV diagram and that on a TS diagram both denote the work that is done by the system undergoing that cycle. And even if the system is a flow system, then this area would denote the specific work, that is minus W dot CV. So W dot CV in our notation is the rate of work done on the system, and minus W dot CV is the rate at which the system does work. And minus W dot CV over M dot is what we'll denote as the specific work done by the system, and that is also the area enclosed by this cycle on a TS diagram or a PV diagram. And this is because a flow system can also be analyzed by considering a parcel of a control mass as it undergoes various processes in different equipment. And one thing to note is that here, throughout our discussion, we are assuming negligible changes in kinetic and potential energies, which in practical applications are negligible. So understanding the work done by the system executing this Rankine cycle in terms of the area and the heat that is transferred in terms of the area under the respective paths is important, and we'll show that also in the next lecture. But here we note that if we want to calculate the thermal efficiency of this ideal Rankine cycle, then that is equal to the net work output over the heat that is absorbed, let's say, for a unit mass of substance undergoing this cycle. And this is equal to the area enclosed by this curve, that is from 1 to 2 to 2 prime to 3 to 4 and back to 1, divided by the heat that is absorbed, and that is the area under this path going from 2 to 3, and this is the heat that is absorbed. So the area, we can denote these points as, let's say, A and B. So this is the area enclosed between this polygon, that is A to 2 to 2 prime, 3 to B and back to A. So this picture of the thermal efficiency of the Rankine cycle would be helpful, as we'll show in the next lecture, where we'll consider the effect of increasing the temperature and pressure at which heat is absorbed or decreasing the pressure at which heat is rejected in the Rankine cycle on the thermal efficiency. And there we'll see that interpreting this efficiency in terms of the ratios of these areas would be helpful. For analyzing the Rankine cycle, it is helpful to think of the efficiency as that of a Carnot engine, but with average temperatures at which heat is being supplied and rejected. Now, due to the change in this pumping process, where we now are pumping this liquid from state 1 to state 2, this heat that is added over this path from 2 to 2 prime is being added to subcooled water at a lower temperature than what it is added in a pure Carnot cycle over this process 2 prime to 3. Therefore, the average temperature at which heat is supplied to the Rankine cycle is less than that of a Carnot cycle. Therefore, the efficiency of the Rankine cycle is lower than that of the Carnot cycle. One practical issue with the Rankine cycle that is shown over here is that the steam that is exiting the turbine, that is from state 3 to state 4, we have an expansion process such as in a turbine, and the steam that exits the turbine at state 4 has a moisture content. So at state 3, the quality of steam is 1, but here the quality is less than 1. That means there is some moisture in this steam. In practice, the quality at the turbine exit should not decrease below 90%. Otherwise, because of the moisture, not only does the turbine efficiency decreases, but also moisture causes erosion of the turbine blades, particularly at the low pressure stages of the turbine, that is near the exit. Therefore, in practice, the quality at the turbine exit should not decrease below 90%. If we look at this basic Rankine cycle and we try to have heat addition at a higher temperature and higher pressure, such as shown on this green color, then if we expand the steam, then at the exit the quality would be lower compared with the case where the heat is being added at a lower pressure. So this heat addition is at higher pressure, but because of this shape of the saturation dome, if this steam is expanded isentropically, then the quality at state 4 prime is less than quality at state 4, which is not desirable. So obviously, to increase the efficiency of a Carnot cycle, we need to absorb heat at higher temperature. But when we look at this Rankine cycle, absorbing heat at higher temperature and at higher pressure results in a lower quality of steam at the exit of the turbine. Therefore, to overcome this issue, the Rankine cycle is modified by superheating the steam in the boiler, and this is called the Rankine cycle with superheating. So what is done in superheating is that all these processes are the same. So compared with the basic Rankine cycle, these processes remain the same, but now in the boiler the substance is heated so that it is not at this saturated vapor state at state 3, but it is superheated. And this is a new state. So note that this is again heat addition at constant pressure, and this is how an isobar looks like. But state 3 prime now has higher temperature than this saturation temperature. And now you see that if we have steam at state 3 prime, that is a superheated vapor, and now it is expanded in a turbine, then we get significantly better quality, and in fact we can also have a superheated vapor at the exit or a saturated vapor at the exit if we further superheat this vapor. So this cycle shown in the blue color is called the Rankine cycle with superheating. So clearly now, due to superheating, the heat is being absorbed at higher average temperature compared with the basic Rankine cycle. Therefore, the efficiency of the Rankine cycle with this superheating is higher than that of the Rankine cycle without superheating, that is the basic Rankine cycle. And another advantage is that superheating results in improved quality at the exit of the turbine. So now that we understand what is the basic Rankine cycle and the Rankine cycle with superheating, we can now analyze the Rankine cycle, and we look at first the basic Rankine cycle and determine the work output and its efficiency. So consider that the working substance, that is a unit mass of working substance, is at state 1. Then what we need to know is that what are the pressures at which heat is being rejected, that is this condensation process from 4 to 1 is taking place, and what is the pressure of state 3. So if these pressures are known, then we can analyze this ideal Rankine cycle, which is the basic Rankine cycle. So the way to do it is that, so if we know pressure P1, then we know that at point 1 the quality is 0 because the substance is at the saturated liquid state. So we can look up at the tables or through software and we can determine the enthalpy at state 1. Now we know the pressure, which is same over this process 2 to 2 prime, over which heat addition is taking place, and we also know that S1 is equal to S2. Therefore, knowing that P2 is equal to P3, that is given to us and that is fixed, and entropy at state 2 is equal to entropy at state 1, we have two conditions that are known, and therefore we can determine enthalpy at state 2, knowing the properties of pressure and entropy at state 2. And we can do this by looking at the tables or through the software. But for this compressed liquid state, we can also determine H2 by noting that dH is TdS plus VdP. And if we integrate this over 1, to 2, we get H2 minus H1, and because for this process, for 1 to 2, the entropy change is 0, this is 0, and we have this integral 1 to 2 V dP. Now, for a compressed liquid, the specific volume is more or less independent of the pressure. So if we know the specific volume at state 1, then the difference H2 minus H1 can be simply determined by this expression. So now we know this state 2. So the difference in these enthalpies is the work that is done in this process. This is the work done in pumping the liquid from state 1 to state 2, that is from lower pressure to higher pressure. And this is obviously equal to V1 times P2 minus P1. And this approximation that we have made is possible because the specific volume is a weak function of pressure, but this is not the case if the substance is in a vapor state. This is only for a compressed liquid state. Next, we look at this process from 2 to 3, that is heat addition. So the heat addition can be found out by applying the first law again to, let's say, a boiler which takes in the substance at state 2 and the substance exits the boiler at state 3. Then the heat that is added in this process to a unit mass of substance is H3 minus H2. And then we can look at this process 3 to 4, that is expansion of steam in the turbine. And now we can find the state 3 because we have pressure P3 is known, that we have fixed, and quality is 1 because here we have a saturated vapor. So that's how we can calculate the heat that is added. And once we have state 3, we also know the specific entropy at state 3 because the state is determined by the quality that is equal to 1 and pressure that is equal to P3 that we have fixed. So now we say that at state 4, entropy is equal to S3 and pressure at state 4 is equal to P1, that is this low pressure. Because we know S4 and we know the specific entropy of the saturated liquid and the saturated vapor at this pressure, so we know SF and SG, then we can solve for the quality because entropy at state 4 is given by this, and we know this SF and SG because we know the pressure P1, and knowing that S4 is equal to S3, we calculate this quality X, and once quality is known and we know the pressure P4 is equal to P1, we can determine the enthalpy at the exit conditions. So this is how you'll get the enthalpy H4, and once enthalpy is known, we can calculate the work that is done by the turbine. So that is H3 minus H4, and this is minus W34, that is the work output of the turbine. And lastly, for the process 4 to 1, heat is being rejected. So if we apply the first law to a condenser, we have the heat that is rejected. So minus Q41 is the heat that is rejected, is equal to H4 minus H1. So the net work that is done is the work, this is the work done by the system. So this is minus W34, this is the work done by the turbine minus the work input to the pump for this process 1 to 2. So this is equal to, from here and here we have H3 minus H4 minus H2 minus H1, and this is also equal to H3 minus H2 minus H4 minus H1. So note that this is the heat that is added, and this is heat that is rejected. So as expected, the work done is equal to the net heat that is added to this cycle. So now we can calculate the efficiency. So the thermal efficiency is this net work, that is H3 minus H2 minus H4 minus H1 over the heat that is absorbed by this cycle, and that is H3 minus H2, and this gives us the efficiency of the Rankine cycle. So this analysis that we have done is for a basic Rankine cycle, but if we have a Rankine cycle with superheat, instead of these state 3 we'll have 3 prime, and state 4 we have state 4 prime. So the only change in our analysis will be that then the instead of enthalpy at state 3 we'll have enthalpy at state 3 prime, and enthalpy at state 4 will be 4 prime. Consider an example where you are given that, let's say, pressure P1 is 10 kilopascal and let's say P3 is 2 megapascal. So if you are asked to calculate the efficiency of this basic Rankine cycle, that is 1 to 2 to 2 to 3 and 3 to 4 and back to 1, and you are given that the boiler pressure is 2 megapascal and condenser pressure is 10 kilopascal, then that's all you need to know to determine all these states 1, 2, 3 and 4 the way we have described, and then you can use this expression to calculate the efficiency. Now if you have superheat, then in addition to this pressure that is 2 megapascal, you also have to specify the temperature up to which the steam is being superheated. So let's say if this temperature is 300 degrees Celsius, then you can determine this particular state, because now you know this pressure 2 megapascal and you know the temperature of this superheated vapor at state 3 prime. And once you know pressure and temperature, you can calculate the enthalpy and specific entropy, and this specific entropy at state 3 prime will be equal to the specific entropy at state 4 prime. And knowing the specific entropy at state 4 prime and this pressure 10 kilopascal, you can also determine all the properties at state 4 prime, and therefore you can calculate the efficiency of this Rankine cycle with superheat also. So I'll leave this calculation as an exercise for you. So what you can do is you can calculate the efficiency of the basic Rankine cycle and the efficiency of this Rankine cycle with superheat, and the conditions are that the boiler pressure is 2 megapascal and the condenser pressure is 10 kilopascal. And for the Rankine cycle with superheat, the state 3 prime is 2 megapascal and 300 degrees Celsius. For these two cases, you can look up at the steam tables to find the properties of water, and you can calculate the thermal efficiency. So if you go over this whole process and plug in the values, what you will get is that if you have the basic Rankine cycle, you will get an efficiency of 30.3%, whereas with superheat, for these conditions that I have given, you will get an efficiency of 31%. And I leave this calculation as an exercise for you.